I'm here to introduce Professor Adibi on behalf of Dr. Katira. He had a last-minute commitment, so he couldn't be here. But for those of you who don't know me, my name is Jordan Yusuf. I'm a professor of mechanical engineering and a colleague of Dr. Adibi. So it's my pleasure to introduce her. So as I said, Dr. Adibi is an assistant professor of mechanical engineering at San Diego State University. Before she came to San Diego, she was an assistant research professor in the Center of Advanced Vehicular System at Mississippi State University, a postdoc fellow at Texas A&M, and another postdoc fellow at Texas, Austin, and Houston, and the University of Houston. There's a lot of things here. You have a half an hour. I'm going to read all this, okay? She obtained her PhD in mechanical engineering from National University of Singapore in collaboration with the Institute of High Performance Computing. She received a master and a bachelor degree in mechanical engineering from Isfahan University in Iran. And now she works in data-driven and physics-based multi-scale material modeling. So please join me to welcome Dr. Adibi. Thank you.
Hello, everyone. Thank you so much for attending, especially at this Friday afternoon. And thank you, Dr. Yusuf, for introducing me. I'm going to talk today about some of my research in computational mechanics lab in the area of multi-scale material modeling and design. And specifically, I'm going to talk about computational design for next generation of damage-tolerant material. Okay, he has already introduced me, but just as a slide, I did my bachelor and master in Isfahan University of Technology at my home country, and I received a single scholarship and I moved to Singapore, and I did my PhD at National University of Singapore in collaboration with the Institute of High Performance Computing over there. Then I moved to US, and then I did my first postdoc at University of Houston in the Department of Civil Engineering, and then I moved to UT San Antonio, and which I did my second postdoc in the Center for Non-Colloquium Phenomena, and from there, our group moved to University of Austin, Texas at Austin, and from there to Texas A&M University. I was in 3 places in Texas. Then after that, I got a research faculty position, and I moved to Center for Advanced Vehicular System at a very small city named Starkville at Mississippi State University. And after that, I moved to San Diego 2 years ago. And right now I'm an assistant professor in the Mechanical Engineering Department at San Diego State University. Okay. As I've told you, my research is mostly in computational mechanics. Let's see that how computational mechanics has changed the engineering design over the sector. In a century ago, like a long time ago, most of the engineering design used to be done by the trial and error, which, as you know, is really expensive and time-consuming, and also sometimes people are willing to risk their life also to do some part of this experiment. Okay, of course, it's okay. One of the examples of the using engineering design and computational power in aviation sector. And nowadays, because of the power of computational mechanics and computational modeling, it's easy to construct all these engineering design by computer, and then it makes all the design faster and much more cheaper, of course. And as you can see, this is one of the branch of the years ago. Shows about the Boeing and the Dreamliner. That is the animations. Just to show you that how computational mechanics can revolutionize the area of engineering design, and hopefully in the future It can be all these computational power and data science and machine learning can help us to design and optimize through all the relevant lengths and time scales. And hopefully come up with some multi-scale models that they are more robust and more high fidelity model. And the advances of the manufacturing and material processing can help us also become in different sectors with the new material that maybe also pave the way for the zero carbon emission by 2050, which is the aim, especially for the California. Okay. Most of these computational mechanics are applied, especially in the area that we have extreme condition. Extreme condition is something I'm mostly dealing with the grand challenging for the engineering that was explained by the National Academy of Engineering. And they are applied in different sectors, for example, in renewable energy, aerospace, defense, and also advanced manufacturing or even medicine. In all these sectors, usually we are dealing with an extreme environment, which can be challenging experiment or complex physics that is coming by the high pressure or high temperature or very high strain rate loading. And basically, it's difficult to do those experiments, and computational mechanics can be of a great help. Okay, my research interest is mostly in data-driven and physics-based type of multi-scale material modeling. Basically, I'm trying to model the material behavior and come up with some design and discovery or processing of the newer advanced material. And it can be like for the designing material that can be damage tolerant. And this idea, the initiative comes by the Material Engineering Initiative, which was launched about a decade ago. And the idea, the aim behind that is just come up with discovery and deployment or manufacturing of the material with faster speed and cheaper as well at the same time, which can be used in different sectors, like in clean energy, human welfare, and national security, and totally it's helping for the to improve the quality of life. To just summarize, mostly for any multi-scale material modeling in any sectors and any those applications that I have already taught, we are dealing with the different time scales. And we can get data and models based on different from these different time length scales, and come up with some multi-scale model that can predict material behavior or design a material that can give those properties. Okay, talking about these different time and length scales. Usually in the computational mechanics, when we are talking about multi-scale material modeling, we are dealing with different length and time scales, and we have different methods that can be used for each different scale. Like for example, when we are talking about the electrons and their reaction, then we have ab initio and quantum mechanics. When we are talking about the interaction of atoms, it could be atomistic or molecular dynamic simulation, and we are going to the much higher length scale, like continuum-based or macro scale. Then it would be finite element modeling or mesoscale type of modeling or continuum mechanics. And at the end, by having all those information, machine learning and data science will help us to just optimize the model that we have. But today, I'm going to talk about the atomistic and in the simulation, one of the methods in 2D multi-scale type of modeling. And I just briefly will explain what is the simulation, because I think that you are from different background and maybe not all of you are aware about this type of modeling. And then I bring two types of examples that helps for the predicting the failure of material by using the MD simulation, which is one of them is talking about the fault failure, and the other one is designing of the non-engineering solid glass or non-glass material. Okay, just some introduction about MD simulation or molecular dynamic simulation. It's basically a tool that helps us to predict material properties based on just the interaction of a very fundamental atomic interaction. And the idea is just try to mimic, by the simulation, try to mimic what atoms are doing in the real world. Try to find the trajectory of atom over any environment or any loading situation that is applied to the material. And we have two basic things in this simulation. Usually we are dealing with the energy function that that led us to see the force that is experienced by the atoms based on their position. And using and having those energy as a function, we can just use the Newton law to just see the effect of those motion of the atoms and try to those motions. Just see that, for example, we have a system of n atoms. We have a system of n particles, each of them has mass n, and its initial configuration, and initial position of those atoms, and initial velocity of those atoms. Then we can just form an interatomic energy that predict the energy of these atoms in this system at this special position. But these atoms are applying force to each other, which is equal in the opposite direction based on the physics that we know. And this force can be related to the distance of the atoms in the space. If they are so close to each other, they pull each other away, or if they are far away, they just attract each other. And based on this distance or coordinate of atom, we can have energy, define an energy function for the system, and from that energy we can get the derivative, which gives us the force. Then if you have the force for the force that this system, each atoms are applying to each other, then by the second Newton's law, we can just get the acceleration. And from the acceleration, you can get the velocity, and from the velocity, you can get the position of atom. And basically, we have a system of equation, and second order differential equation that can give us the position of atom at each time step. Then, as a computational scientist, of course, you know different numerical integration methods that can solve this type of equation. Basically, in the computational method, just you divide your system to different time steps. Each time step, you see the position and velocity of the atoms, and then you get the energy. And based on the energy, derivative of energy, you get the force, and from force, you have acceleration. And then by numerical integration, you can have the position of atom at the next time step. If you follow, and after, like, for example, t, second, you have the position, the final position of your atoms. Okay, then you can use different type of numerical integrations. This is the flow chart that I have already mentioned, getting the position and velocity and force, and then from that having the next velocity and position of the atom. One of the methods is using the Euler method or any type of method, just writing the velocity and next velocity of the atoms, and just instead of the derivative of velocity, you can just get acceleration, which comes from the force, and the same for the position. And the basic idea behind all those and this simulation and setup is the same flowchart that I have, the simple flowchart that I have already explained. It's just getting the position of atoms, velocity, acceleration, and from the force, and then back the energy of the atom. And the things that usually we do in the setup is just to feed the initial structure of the atom, just minimize to get to the basic, to the lower energy time scale, and then apply any type of thermodynamic procedure that you want to heat your system or apply some load or some other thing, temperature or pressure or volume, and then get your result after some step, and then another. One of the software or package that have been used widely for this simulation is LAMPS, which is open source package, and has been generated by Sandia National Laboratory and can predict and develop the material in a good range. Okay, then I've already summarized what is the simulation. Yes.
How does dissipation fit into a molecular dynamics framework?
You mean dissipation of the energy?
Yeah, dissipation of energy, not irreversible processes. So, I mean, you have a potential function. Right?
Yes, the
And
potential.
some of the energy involved with that.
It depends on how well developed is the potential and how it can consider any type of things that is really happening in the physics background, the physics. And some of the potential fire are really easy, like EM type of potential, just kind of consider the interaction of the atom and just the energy based on the position of the atoms. And they might consider some dissipation that happened during phase 5 entry or some other type of thing that's not based on the just some other terms that they consider in the when they are treating those parameters as well.
I like it. Is there any way to do something like this to solve this systems like this compact finite difference scheme for solving PDEs and such?
Sorry. And would
What's
you
the
please
question?
repeat it?
Can you please repeat the
Is
question?
there any way to solve them like this, about the algorithm? Is there any algorithms that are like this compact finite difference algorithm solver for PDEs?
I think that would be a good question to discuss with the professor after the lecture.
Okay. Then I just summarized what we had about empty simulation. Then the next step is just bringing some example about using this empty simulation for design of material. One of the examples is just talking about small failure and the design for the armor. And the question is that, for example, what do you consider when you want to design an armor? What is the criteria that is important? Since it's an armor, we are dealing with the highest turn rate type of loading and impact or different type or rate of loading. Then the material and microstructure of material is really important. The defect that we are generating the material is important. And one of the strategy is just look at the microstructure and see that what is happening when we are dealing with this highest turn rate of loading, or for example, this impact that's happening for the armor or different defense application. As I have mentioned, we are trying to use ND simulation, the proper ND simulation to predict this failure of the mechanism that is happening during a small. Okay, impact, the damage of impact depends usually to the velocity that this impact is happening and also different time scale. It can be as easy as carries between the trade or barricading that is just destroying a house, or simply as the accident that can cause some failure. Or some bullet that is from the World War II, or just some armor attack that is used in the war, or just materials coming to the earth to destroy dinosaurs. Then in all these scenarios, we are dealing with some impact that just transfers some energy. Just to dissipate the energy from the material will go through different microstructure. Different scenario will happen. For example, we might have a crack or fragmentation in the material. We might just have a small failure, or just the energy it might be so high that can just go above the melting temperature and cause the phase transformation in the material. Now we want to look at the small failure. Here is one of the samples that has been sent by the European Space Agency. It just shows some of the space debris that are hitting an aluminum plate, and you can see that also that this is small sphere hitting this the aluminum plate. If the plate can avoid the penetration of the bullet, but at the other hand, it cannot avoid the effect of a wave propagation. Those waves are coming through the plate, and at some point they cause some failure in the material that can be seen here, and we call it a small failure. Then we want to see that how we can predict or control this small failure. This is another thing that shows that, for example, we have the impact of the flyer to the target. At the place that the impact is happening, the waves are propagating, and when they are coming back as a tensile wave, they are hitting at another place that this small is happening. If we look at the microstructure of the material and look at the experimental data that we have, the place that this small is happening, this is a sample for high purity single crystal aluminum. We see some dimples on the material. Then we want to see that what is the source of these dimples that we can see at the place that the small is happening. If you just remember from engineering material, we have already passed those. We have different type of defect in the microstructure. One of these will be these vacancies, which we are losing one of the one or some atoms in the microstructure of the material. It has been seen that for this whole process, when we have those high intensity shock, and those are usually produced at the place that we have damage, they produce a high percentage of the vacancies in the material. Then these shock loading or induced super concentration of vacancy, which finally can due to the spall failure. One of the hypotheses is that these shock loading can generate a super concentration of vacancies. Those vacancies are clustering together and make a larger cluster of the vacancies, which is a place like a non-void formation that is a place for nucleation of the fracture and happening of the spall. This phenomena is so much dependent to the time and also to the temperature that we are applying. The temperature can make this diffusion faster, and also the time also make it easier to create a larger form. Let's see that what we can do with the MD simulation to just do this process. We started with the just perfect aluminum cluster, aluminum crystal, and then randomly remove some percentage of atoms to just give some percentage of vacancies to the structure. The second figure is just it's the sample, just those dots are showing the vacancies. Just for the purpose of the visualization, I just remove the rest of the item and just show those vacancies by the point. Then after some time, if we look at this microstructure, if we give it enough time, we can see that those vacancies are clustering together and make larger clusters. And we can look at the distribution of this cluster over time and how their size is changing over time and what is the percentage of those vacancies at each size as well. Then we can just apply some loading on the sample at different time steps to see that how the larger cluster size would affect the strain of material, or this microstructure that is happening after shock loading is affecting the material properties. Okay, just visualize the process. We have started with the initial condition, just removing 1% of vacancies and giving the structure time to evolve to the time, and then we can see that those vacancies are clustering together. At each different time step, we are applying hydrostatic loading to the sample and then draw a stress strain curve for the material to see that how material would fare and what is the spall failure, which is the maximum stress of the material through the simulation. We did this modeling simulation for different time steps. At each time step, we got the microstructure and applied load, hydrostatic load, and got the stress strain curve from the simulation. We run it from 0 nanosecond to 100 to 500 nanosecond. And then we got the spall strain or the maximum strain of the material extracted from those data. Then you can see that the strain is decreasing, and as we increase the clustering time. Then this it shows that by increasing the clustering time, we have a larger cluster size, which can decrease the strain of material. Okay. We wanted to see that if we can just model this scenario with just larger cluster size. This way, having the larger cluster size without the distribution of the cluster, if we can predict the material behavior. Just to compare, we have a system with the distribution of vacancies and another one just with the larger cluster size. And we apply loading to both of them. This is the first one with the vacancy clustering, and the second one just by the single void with the same size as the larger cluster size. We got the stress strain data for both of them, and then we put those data on the same curve. And basically, they can match a little bit. I mean, in most areas, they can match in a good sense if we want to just build up a model based on the larger cluster size. Then we used these data, just we are trying to develop a continuum-based type of model and improve the model that we have. This is the data that continuum level model that we have generated based on the dislocation emission from nano-core display phase. And we are trying to use this data as well. You can see that there is a good balance between those continuum model, except for the very small cluster size, with the one that we have already from MD simulation. And if we give enough time to the clustering process, it can give the same data that we have. Then the next step that we are doing is just changing this part of the continuum model.
Does the clustering process require the material to be stressed highly?
If we apply stress, of course, it will be faster. Because to see something at this scale and at this time scale, we apply force, which is something that is happening also at the shock stress. The material is under stress.
So material that was unstressed might do this, but it would take years or something like that.
If it might not happen, or it just take a lot of time. It depends on the temperature as well.
One more question. I mean, these impacts don't induce hyperstatic stresses, right? They're very.
You mean that yeah, it cannot be, it's more uniaxial if we are talking about type of impact, but here, because we wanted to have a model to look at it. It's not exactly modeling the shock. It's another thing that I'm doing right now is just really modeling the shock and see that what is. Here, we just wanted to use some continuum-based type of model to just predict and know the mechanism that is involved for the shock model. It's not exactly looking at the shock and try to mimic exactly the things that is happening in the shock. We see that what is the mechanism under that is frequencies and the clustering frequencies, and consider that one as a part of the continuum of this model. Then, okay. Then the next step would be just how to avoid this. This is something that right now I'm working, and just one of the ideas is just by using some secondary elements in the material, maybe we can just slow down this clustering process, or just putting some grain boundary or some other idea that we can just design the microstructure of material to make a cavitation resistant material. Okay. Then this is the first example. Just to take away, we have introduced shock wave, and we introduced shock wave modeling, and just that after shock we have a super concentration of vacancies. These vacancies may cluster together and just form a type of nanowall, and which can finally cause the failure, inductive failure of the material. And by getting some information from every simulation, we can come up with a framework and a atomistically informed type of framework to model this behavior. Okay. Any question from this one?
I have two questions, please. So the first question is, when you are propagating a shock wave in a uniaxial state of strain, you are generating a hydrostatic stress. So your results can be interpreted in that sense. But I noticed that the results you're getting are still far away from the intrinsic strength of aluminum. So if you calculate like what is the intrinsic strength of aluminum, even accounting for clusters, you're getting way below that. So you're getting 4 GPa, right? And we know it's a lot more than that, like E over 3. So if you take the modulus of aluminum and you divide that by 3, you're getting a lot more than that. So where's that dichotomy between the numbers you calculated or the number you're predicting and the intrinsic strength of the material?
I think it's mostly because of the rate of loading that we apply. Of course, in MD simulation, the rate of loading is very high, and we need to keep it high because of the computational resources that we have. Of course, just from MD, we can mostly get a trend. We don't get an exact, like a real number. Otherwise, that we have some experimental that we can run at this high speed rating, or we can decrease the speed of rating. And we have a very good, also the accuracy of the result that we get also so much dependent to the potential phi that we are using. If it can predict like the properties in a really that can be just exactly as the experimental data that we have. We can get a better result.
I understand the point of the difference in the loading, but when we talk about the intrinsic strength of the material, the intrinsic tensile strength of the material, we actually are not, I mean, we're talking about a very, very fast loading because that's the only way to suppress all plastic deformation and just give rise to the intrinsic behavior. But anyway, so I point taken about the loading, but that's where this comes in, this graphs come in. So my understanding that these stress strain curves at different time, right? That one that you're showing right now, different.
This one?
Yes.
At the top, yes,
Yeah,
at
so-
different
so-
clustering time.
Different clustering time. Okay, so if you have a different strength as a function of clustering time, that indicates that there are time-dependent processes going on.
Yes.
So from your results, what are the fundamental mechanisms that leads to these time-dependent processes?
The clustering is already time dependent. The total clustering, I didn't bring the whole data. I did a simulation for different temperature and concentration for different time. To just model this time dependent, of course, it's really time dependent. If we give enough time, then we have this process and the size that really we need to see this type of fracture, it should be really high. Did it answer your question or?
Thank you.
More question? Okay, the next example that I want to show is about talking about another type of material, which is metallic glass material. These materials are having combination of the properties of both metals and glass material. The element is like metallic material and the microstructure is mostly like glass material, is amorphous. And they were synthesized for the first time at California Institute of Technology by fast quenching of the molten alloy. For example, at the rate of 10⁻⁶ Kelvin per second. At that high speed, usually atoms don't have enough time to arrange themselves in the crystalline structure. Then the final structure would be amorphous. Because of this amorphous structure, usually they have some special properties. They have very high specific strain, they have a very high yield strength, high hardness, and superior elastic limit. Their elastic limit is very high. They have a really good bouncing effect, high corrosion, and high wear resistance. For example, and some of the application that we can consider for those is like because they have a really good bouncing effect, we can consider just, for example, if you drop your phone, it's made for that, and it goes back. It's a very ideal case. But because of the very good corrosion and wear resistance, they can be a good candidate for the medical device, or because of the very high elastic limit, they can be a good candidate for a sporting good, or because of their fine structure, they can be a good candidate for NASA application as well, which has been used a while ago for this different type of application. But like other material, when they have a very good properties, usually they have some backbone as well. And what is the Achilles heel of this type of material? They usually vary to a very dominant and very shear band formation that makes them really brittle material. These are some of the experiments that show the formation of shear band in this type of material. Then we want to see that what are the approach to improve the ductility of this metallic glass material and to avoid this localized plastic deformation or shear band formation. One of the methods is just using some nanocrystalline inclusion, like just putting another type of element that can just be used as a source for the nucleation of this shear band, and then totally distribute the shear band formation and give more plasticity to the material, or doing some plastic deformation and cold work just to distribute this shear band formation. Another one that I'm going to try is forming nanoglass material. Okay, these nanoglass material are made by the constellation of those glassy grain, just a small glassy grain. We just compact them And you can see the final microstructure have glassy grain that are separated by the interface. Nanotomy is something like nanocrystalline material, and the difference is that for the nanocrystalline material, we have a grain that have different crystalline structure, which are separated by the grain boundary. But in the nanoglass material, we have grain that they are already amorphous and they are separated by the interface. But the microstructure properties of the interface are different from the grain. Then now we want to see that if really this microstructure, nanoglass microstructure, can really improve the plasticity of metallic glass material. We use again in this simulation, and the structure that we have chosen was copper zirconium and the nanopilar copper zirconium for the different grain sizes, and we started with the just crystalline material of copper zirconium, and then we melted to 2000 Kelvin, and then fast quench with the rate of 10 power 10. Of course, the rating and the cooling rate is much higher than the one that is in the experiment, but it was the one that we could afford for those type of samples. And then we just replicate those material and relax it and just apply some pressure to make the sample size that we are looking, and then using the boron-active solution and some hydrostatic compression to just to remove any type of the pore that we have in the microstructure. Then we had the structure of the nanoglass. Then we cut the nanopilar from this nanoglass. We have the nanopilar with different emitter. And we applied uniaxial type of loading to the microstructure, to the nanopillars, and then try to see that how this nanopillar with different grain size would deform under uniaxial loading. Okay, these are the results that we got from the stress strain curve. You can see that this is a metallic glass sample, and those are the results with the nanoglass with different grain size. The sample for the metallic glass, as you can see, it shows a very sudden failure, which is the indication of the shear band formation in the material. But as you go to the nanoglass material, this shear band formation is decreased, and also at some point you can see just some superlative points for in the material. And then, but of course, like the other type of engineering design, at the expense of getting some plasticity, we are decreasing some of the strain of material. Here, show that how the strain is decreasing with the grain size as well. And okay, but let's see at how the deformation of this metallic glass and nanoglass are compared together. Here is the result that we see under uniaxial loading. The top one showing just the metallic glass that is failing to the formation of very high rapid shear banding. And then you can see that as we are going from the metallic glass to nanoglass, we have some plasticity formation because we can spread the formation of this shear band, and we have a network of shear band. And then finally, we can see some type of necking behavior and plastic flow as well. Then we also had a collaborator in Germany that did some of the experimental work as well, and we could see that from the experimental results as well. We see that for the metallic glass sample, if it plays, shows that that one is breaking through shear band, and that one to some necking, and you can see this the strain that it can tolerate would increase under the nanoglass samples. Okay, one of the other idea was just also combine this metallic glass and nanoglass and make a composite of those, and just having different layer of metallic glass or different layer of nanoglass and metallic glass, just to work with the properties, just to tune their strength and also their plasticity. And these are some of the results that we got just by the metallic glass, the nanoglass, and layered metallic glass, just to try to work with the strain and also the activity of the material. And totally just going from metallic glass and changing the microstructure of the material to nano glass, we could see a transition from the very localized plastic deformation to some plasticity and some type of thinking. Then the takeaway from this point is just we introduce that how by changing the microstructure and implementing some type of interface in the microstructure of the material, we could separate the shear banding, a very dominant shear band formation, and we could transit to the lifting in some type of homogeneous flow as the grain sizes are like this. Then totally by working on the grain size and the network of these grain boundary, and we can, or with making a composite of those materials, it's possible to tune the behavior of the total metallic glass and hopefully getting some plasticity and also a good strength of those materials. Okay, totally today I've talked about computational mechanics. I went through this molecular dynamic simulation and it's around 2 examples from this spot failure and also non-obvious materials that explain this type of behavior. And that can predict the behavior of material by using input simulation. This is just an overview of the things that we are doing in lab, different materials, and just using this type of analytic state modeling to predict behavior. If you have any question, I would be happy to answer.
Not sure how this works, but I'm gonna do it my way. So if you have a question, please use your hand. Stand up, you have to field the question. Thank you for the engaging talk, very interesting work. I can maybe start since I am moderating. If you go back to your nanostructured glass, so since you calculating, are you seeing a different flow mechanisms? Have you tried to probe the stress triaxiality to see, you know, the relationship between this uniaxial loading that you're doing and how that changes the stress distribution or the stress transformation?
We did some type of just looking at those things as well. I don't recall exactly, don't have the result right now. We're looking at the microstructures, just looking at the free volume as well, how those things are different at the interface and also grain boundary. We did a small study on the stress structure, but not a very intensive one, but that's a good idea.
Other questions? Yes, Professor.
So for both parts of your talks, you've done a model. What are sources of uncertainties in both of these?
Of course, they are just a model. I think there are so many things that is happening on the result. Like for example, as I mentioned, like other type of modeling and the loading situation, the potential file that we are using, and we just really idealize the system by this type of like the microstructure that we have generated. There are different sources that make it not to be exactly as accurate as we want, but just we wanted to get some grant to have some idea about the things that is happening by changing the infrastructure and some idea about the predictive type of model.
Has to do any sensitivity of your conclusions to those?
Sure, that would be a good plan to do. I haven't started, but it would be really nice idea to just start.
How representative your model of the crystal structure of the materials or the distribution? So when you like select the size to be 3 nanometers or 5 nanometers, and how is that comparable to experimental? I mean, the actual material.
It's really difficult to go to 3 nanometer, of course.
Yes, yes.
So I think these are just, as I said, because if we really want to make a model that it's comparable to the experimental one, it's really, we really need a very good computational power and all the resources. 20 nanometer maybe is something that we can compare, still depends. 20 nanometer, but of course, 3 and 5 is really small to the things that we have in experimental method. Yeah, these are some of the things as well. The time and length scale also is always issue for the presentation.
Yes.
How long do these simulations take? Like days, weeks, minutes?
Sometimes weeks, it depends on which part of the simulation, but sometimes weeks. I think I had about like 100 million atoms in one of my samples that takes a week or so.
When you introduced metallic glass, the way they formed it was this quenching at some really high rates.
Yeah.
Given that you have to achieve that high rate of quenching, what is practically the size of scale at which you can produce a part today? Can you produce a car axle in that stage, or are we talking about what scale can you quench? Or are there other methods that
Right now, in the experimental thing, they have really the nanopillar of the metallic glass. They are doing experiment, but maybe in nothing industry, but they have those sizes already in place.
you can produce them at
Yes.
scale?
And in Caltech, one of the professors that I was working, they are working with these nanoscale.
Because then it can be from quenching, right? The quenching, when you go to heat transfer, it becomes quenching time scales. If we get that high quenching rates on big ones.
I think so, I'm not quite sure, but yeah, I think so.
And yeah, that's a good question about the scale of the actual production. That's they work on the nano things on.
No, I know. You see,
Yeah, I can.
where's the technology?
Yeah.
It's good to do the simulation to know where we're getting then from the other end from manufacturing. You have to, because I always look at heat transfer as a fusional process that's so slow. And even some of the things that you showed with vacancy migration, it's a diffusion process and the rate seems like, I don't know.
Usually they do like, I think with the spin, in a melting spin experiments, or they do usually manufacture small artifacts. So micro, nano, I think Khalid actually, Morsi in chemical engineering have come up with what you call ballistic manufacturing, but it's only for thin films, you can, whiskers, things like that. So really, I think the scale, I don't think you're at the point where you can make larger scale. You're talking about very small artifact, micro and nano scale, where you can actually achieve such high quenching rates, such high, control over the microstructures and things like that. I think this is from my limited understanding of it.
Just a nuts and bolts guy, I want to see where can I?
Me too.
How many can you make? So I can use it?
Let's go back to the fundamentals.
All the same vein, I mean, are they trying to manufacture things that are composites, fibers, or something like that? They would have a similar tensile strength, but made out of components small enough.
Discontinuous fibers are really important, but discontinuous composites are very important. I think this is more of a metallic composite, like using grains, I don't know.
Yeah, it's just showing the, in the manufacturing process of those non-composite, I don't think that is still in the manufacturing process. It was just showing that how we can really just tune those properties if we want to go.
Somebody's got
Yeah.
manufacture at some point, if you want to go into it.
That would be me and Sachi. Any other comments or questions? Yes, please.
So this is kind of just exploring conceptually, because I don't know if I missed it or if I just couldn't wrap my head around it. But on the first part of your presentation, talking about the actual stall failure and that the relationship of that's the vacancies or the voids in those RVDs that you had. What was the cause of that, or what was the relationship between that impact that caused those voids or those?
After just having those shock waves through the material, usually those shock waves are producing a super concentration of vacancies. If it given enough time for those frequencies at those shock loading temperature and also the state of stress, they might just cluster together and just form something like nanoclone.
Yeah, there's a lot of mechanisms that will do that.
So it's fair to say the loading induces the super concentration vacancies and also the process of conglomeration.
Yes, the shock loading, the tensile part of shock loading.
Yeah, there's two things. I mean, this is a very complicated topic, right? So the first part is when you are propagating the shock wave, you have the compression phase of the shock wave, which is really propagating forward. So that's where you tend to create a very high hydrostatic state of stress, and the hydrostatic state of stress what causes the voids to start to nucleate. Now, on the returning wave, which is, the returning wave, it pulls that apart. And that's what causes spark plane to start to nucleate. If you have a very high state of tensile stress returning, you actually can take the whole part of, you can take the whole chunk of the material out. And that will become, the depth of that will tell you, what's the strength of the material and all these things. But one of the things that we all neglect is talking about strain. You saw that ball goes through a lot of plastic deformation. That complicates things because when you have strain, you have a high mechanical energy. That mechanical energy has nothing to do except the heat. So now you are doing phase transformation in addition to the stress. You're actually changing the material in situ. So one of the biggest problem is in molecular dynamics. You don't account for all this. So you need an experiment that actually can induce such a high amount of stress with very limited amount of strain. There's only one experiment can do that. Come visit my lab. I have to prepare my lab somehow, right? All right, well, I think we're on time. Very fast. No. So any other questions or comments? This is a very nice work, really nice work. I mean, you can see from the questions that it opens a lot of questions.
So you've been using the LAMPS package. Have you changed anything in it, or are you just using it as is? Or
We have developed some potential just to use it, but for the package, no, mainly we just use the whole package. We sometimes need to add some module or some other things as with it.
you're talking to room of computational scientists, right? Besides the potential functions, what is it about the parallelization? What is about the challenges? Where is the bottleneck?
Oh, you mean that of course, we have used the parallel version just to accomplish all those things. Otherwise, we cannot just go with like pure data.
Where would you like to see labs improve to do the kinds of things you would like to do?
And then the community is evolving a lot. I mean, they are developing the LAMPS package a lot since the time that I was working as my PhD. Since now, it has developed a lot, and it's right now. I think it's using GPU as well, and it gets faster as well. And they are so more type of package, type of other.
Thank you all for attending today. This was very nice. I don't think there's nothing in the back, but I'm judging from here, there's nothing left. The food is like a drop. All right, thank you, guys. Have a nice day. Have a nice weekend.